2, 1. Hi everyone, my name is Siamak and welcome to ACigs webinar series. This is webinar number 20. So it's been 20 months since we started the webinar series for Australasian chapter of the International Geosynthetics Society. And as you know, Australasian chapter covers Australia, New Zealand, PNG and Pacific Islands. So ACigs is one of the 45 or more than 45 chapters of IGS. And IGS is the global society. So this is the IGS website, geosyntheticsociety.org. As a member of ACigs, the chapter, you get automatic membership of the IGS and you can access the technical resources and all the discounts on the events and networkings and the webinars that IGS is presenting. And ACigs.org is our website, the chapter website, and you can become a ACigs member by visiting our website, the membership tab, and it actually gives you all the information. Also, the events tab is telling you all the information about our future events. We record our webinars, this one included, and you can access the recordings of the webinars normally a couple of days after the live event from our website. You can also ask for a certificate of attendance to be issued for you by just emailing info@acigs.org, and we can organize a certificate of attendance for that particular event that you attended. Today's webinar. So this webinar is brought to you by ADE Consulting Group. The website address is there, www.ade.group. So ADE Group is a consulting company in Australia, and they have consulting services. They provide consulting services to the industry in mining, oil and gas, waste industry, and infrastructure, and a lot of geosynthetic services as part of that. So the topic for today's webinar is geosynthetics construction quality assurance in barrier and floating cover application. This is presented by myself, Siamak Paulson, and we have John Cowland. He's joining us today from Hong Kong. John is very experienced. I'll introduce him in a minute. In the geosynthetics world. So welcome, John, to this webinar today.
Thank you.
Just quickly read a bio of myself. I'm a principal geotechnical engineer with over 20 years professional experience in different geotechnical and civil engineering research and practice in the fields of waste management, mine tailings, mine water, and urban development transport infrastructure. Also a chartered engineer, managed multidisciplinary design, construction, and quality assurance projects, a variety of civil engineering fields, including landfills, waste management, also tailings storage facilities, different things with the water storage, earth dams, and also road and transport infrastructure and urban development. Project management skills and technical leadership skills extend to planning, design, schedule, conduct, and coordinate civil geotechnical works from concept design through to construction. And also a quick bio from John. So John is an independent geotechnical and geosynthetic expert based in Hong Kong, as I said, with 40 years of experience. John has provided advice to more than 60 government and private sector clients throughout Asia Pacific region, geotechnical, environmental, and geosynthetic projects. This includes solid waste, landfills, dams, tunnels, mines, deep excavations, slope, soft ground, coastal reclamation, liquid storage and disposal of contaminated soils. He has advised on the use of geosynthetics in all these areas, often in an innovative manner since 1986. John has also provided advice on project management for environmental tunneling and water supply projects for projects up to $10 billion US in value. John is a member of Environmental Geotechnics Committee, TC215, of the International Society of Soil Mechanics and Geotechnical Engineering. And he is the chairman of the Association of Geotechnical and Geoenvironmental Specialists in Hong Kong. He was a council member of the International Geosynthetics Society, IGS, from 2000 to 2014. So he's published 50 technical papers on geosynthetics and geotechnical engineering. I have read this quote from Sir David Attenborough before, but I think it's actually worth reading it again. So this is from David Attenborough. I'm often asked, what is the one thing that would really make a difference? I don't think there is one thing, one single thing. We all live such different lives, but there might be one approach that could make a very big difference indeed. I call it rewilding the world. But in practice terms, it means putting nature at the heart of our decisions. If we can move from viewing nature from something nice to have to seeing it as the most fundamental factor in our civilization, we would make decisions very differently. So thank you. And with that, I go straight to my main presentation. So the format for this will be that I start my presentation. So I think it should probably take around 30 to 40 minutes. And then we go to John, and we have John's presentation after that. Okay. John, can you just tell me if you see my screen?
Yes, I can. Yep.
Okay, perfect.
Perfect.
So this presentation is the topic that I will talk about is geosynthetics construction quality assurance, or as well known as CQA, in barrier application. And then we go to John, and his presentation is more focused on floating cover applications. So you see my contact details there. If you need to contact me for any of discussion about any of the topics that I will talk about in today's presentation, I'll be happy to receive emails after this. And I have sort of two parts in my presentation today. Part one is mainly about geosynthetics material conformance. And in part two, I will talk about geosynthetics construction. And also before I start going through the slides, we had IGS's photo competition in 2019, and this slide that you see here are some selected photos from around the world. The winner is on the sort of center right hand side there. This one here was the winner in 2019 of the IGS photo competition. We had in ACigs a 2020 photo competition, which we shared those photos on our social media and some of our email campaigns. But I think those photos many of them are quite nice photos, and I have used some of those photos in my presentation today, and I'll refer to the people who sent those photos to us. Okay, so introduction to the material conformance. Quality control or quality assurance is all about risk management. And to be honest, this is one of the main messages that I want to convey in today's presentation. So any decision about CQA or CQC will directly or indirectly relate to risk management. So essentially, level of confidence in material quality, conformance with respect to the design, function, or specification requirements. So that's the definition of material conformance assessment. And it obviously varies between applications, if they are critical applications, non-critical applications, and also client risk appetite. So we have to get back to that risk management or risk assessment topic each time we talk about material conformance or construction quality assurance. So let's talk about material properties and some industry references. So the question is, what properties are required? So when you're doing a design or when you are doing a construction material conformance, you need to ask this question: what properties are really required? So we know from the standards such as GRI, the Geosynthetic Research Institute standard specification, we have GM13, GM17, and GCL3 for HDPE, LLDP, and GCL. And they are widely adopted as standard specifications around the world. And as you know, they include minimum values and testing frequencies for key material properties. But it's the question again about which one of the properties of the material are required for that particular application. And as you know, like depending on which state you are doing that design for, or the facility is located, whether it's in Victoria, and you basically use the guideline called BEPM, Best Practice Environmental Management, which is this one right here, or in New South Wales, the EPA New South Wales guideline. In Queensland, that's the DES guideline, and also the NT EPA has their own, and also other states like South Australia also has a different guideline for their material properties and construction quality assurance requirements. So these, each of these guidelines may include additional requirements and different test frequencies to GRI. So we need to consider that when we're doing a design. And also from the test standards point of view, we see differences between ASTM, for example, the American standard, the DIN, the German standard, the ISO, which is the International Organization for Standardization, and also Australian standards. So these include variances that can impact the results. So if we are designing a particular material and we're asking the material properties to meet certain specification in accordance with the ASTM, for example, but we also get materials who have test results according to the DIN or to ISO method, we need to consider that in our design and in our CQA, how we want to assess the material conformance against each of these standards. The next topic is manufacturing quality control. So MQC, or sometimes called MQA, material quality, manufacturing quality assurance. So these are the tests that are undertaken on geosynthetics by the manufacturer, so in the factory. Samples typically recovered at the time of manufacturing and tested at a factory laboratory. So every factory, every manufacturing facility has their own laboratory in-house, and they do standard MQC testing, and the frequency of those testing can vary between factories. So some factories have their own sort of requirements or standards for the frequencies to do the testing on their material. And MQC test reports provided with roles upon or prior to delivery. So when you actually work as a CQA engineer on the site, you can receive the results from the manufacturing quality control before the material arrived on site or after the material are delivered. So adjusted MQC test frequencies can be accommodated by the manufacturers. So as I said, some manufacturers use different frequencies for the testing. Consider what MQC requirements are appropriate for your project. So regulatory guidelines, applications, and related risks, design or service life, which is a very important factor, and also exposure condition, if the material is going to be used in an exposed or in a covered or buried condition. So we should consider these factors when we decide on the requirements for the frequencies. Tests for some properties, for example, stress crack and oven aging, are long duration testings. So when we specify material to meet certain criteria in terms of stress crack or oven aging or any other long duration testing, we need to consider the time period that is required for that test. With all the quality checks in the factory, the material gets packaged, delivered to your site, and as you roll them out, there are still surprises. So defects, as we call them, and they come in different shapes and forms. You know, some of them are gel, fisheye, crater, pimples, crazing, surface blemishes, or scratches. They're often undetected until during installation. So specification should address the presence of defects, for example, maximum acceptable rate of a defect, and how to address them. So we need to, in our specification, we need to address that. So first of all, we need to know that these defects might be present as we roll the material out on site. And then we should have clauses around or conditions around what is an acceptable rate of defect, a particular defect in the material, and also how to address those issues. And again, the other factor that can damage the material, you know, after the material is delivered to site and being installed, handling damages. So the left-hand side shows a photo of a drainage geosynthetic mat that was, you know, QA, perfect material. They arrived on site and a forklift was used to sort of mobilize the material from one corner to the other corner, and the forklift operator wasn't aware of the risk of damaging to this material and how important it is. So as you can see, there were multiple defects found on that material. And also the right-hand side picture shows the geomembrane liner, which was placed. The panel was placed in its location, but due to the high wind in that area, not enough ballast on the material. And as you can see, it has created a lot of creases and folds in the material. So this material had to be brought back and checked for any sort of creases and assessed if it's still usable or not. Now I want to talk about additional quality assurance options. So after the MQC, we get the material on site, but the additional quality assurance option here is actually doing independent sampling and testing. So this is very common in Australia, that we take samples independently from the material and test them in an independent laboratory. So they are undertaken by a party independent of supplier or manufacturer. So typically the designer or CQA engineering consultant will do this exercise. Sampling can be done in factory or at the construction site after delivery, and I'll talk about that in a bit later. So testing in an independent laboratory approved by the consultant. It is important that the independent laboratory is approved before we actually send the samples to that lab. And it provides additional confidence related to the material properties and conformance assessment for the material. The other option or the other method of doing the quality assurance is factory production surveillance, which I'll talk about that in a little bit later. So these measures should be considered and adopted based on the project risk. So let's talk about in-factory sampling. So a lot of factories are located overseas, not in Australia. So as far as we know, other than GCL and geotextile and some other geosynthetic material that are manufactured in Australia, most of the geomembranes and lots of other geocomposite drains and other material are imported to Australia. So the factories are located overseas. Samples from those materials, even independent samples, can be recovered at a time of production. If we can send an independent person to the factory and get those samples there, this actually enables the testing to be undertaken during material shipment. So as we wait for the material to arrive on site, in parallel, the testing, independent testing is ongoing on the material. So the chance of manufacturing defect identification prior to shipment is also higher in this case, because we have in-factory sampling. And if there are any defects identified before the material gets shipped to your site, and also earlier results and reduced risk of risk to the schedule. So that's another advantage. However, we need to, basically consider some concerns here, such as costs. Obviously, having someone in the factory will have some costs associated with that. Also, fluidity of the manufacturing timing. As we know, the manufacturing timing are very fluid. So you normally get a window of the production for your material is going to be between this date and this date. And as you get closer to that date, it changes very frequently. So the other factor to consider is manufacturing is 24/7 in most factories, but independent testing is like 8-hour or 12-hour days. So it is very difficult to have 24/7 surveillance in the factory or sampling. Independent laboratory located in manufacturer's country or in Australia. So this is another topic I'll talk about it a little bit later, that some independent laboratories are located in the manufacturer's country, and we need to consider certain elements there if we want to decide to go with that option and testing them overseas rather than in Australia. The other approach is sampling on site. So basically, this is undertaken after delivery to site. So material comes on site, and the time frame for testing often more than 4 weeks. So we need to consider that. So the material is on site, but we can't use them because they're not approved for use until all the test results are back. And that's obviously impacting the schedule for the construction. It requires additional material handling, and there is a risk of damage and cost associated with that. Schedule implications, as we talked about, particularly if material is non-conforming. So if you waiting for the test results to come and then there is a failure there, then that means you can't use that material. We have to go through the process of checking what has gone wrong with the material, and also reduced Qaqc concerns compared with factory sampling. So in terms of the Qaqc or chain of custody, that there is a benefit there. Some additional consideration. So again, we talked about laboratory accreditation. So in Australia, we refer to National Association of Testing Authorities, NATA. But there is mutual recognition by International Laboratory Accreditation Cooperation, which is ILAC. So as I briefly talked about, there are independent labs in other areas, in other places around the world that have this mutual recognition by ILAC, and we can potentially look at using those laboratories, especially with the COVID impact on sending people or travels between countries. This is now an option for the designers to consider. Laboratory testing regime and methods compared with material approval criteria, and are they the same? So we need to make sure that the testing regime is in accordance with the approval criteria. So transport of samples and associated chain of custody. Again, if we are doing sampling, we need to consider that chain of custody and the transport of samples. So we see this a lot in terms of like material handling and transport to the lab, and if there's a GCL, for example, losing some of the bentonite during that time, during the transport time, or the geomembrane is delivered to a lab and we receive a phone call from the lab manager saying that the material is here, but there are a lot of scratches on it. So that's another thing to consider. So I want to talk about the factory surveillance on this slide. So visual assessment or surveillance in factory. So it's undertaken basically to assess the factory QA and production process. It can help and enable detection of production problems or defects, as we mentioned. Potentially undertaken in conjunction with factory sampling. So you do the surveillance and the sampling at the same time. And short duration visits or full-time duration during the production and costs associated with that. So if you want to cover that entire 24/7 production, that's something that we need to consider. And they're undertaken by experienced people who understands the manufacturing process. So that's another important factor to consider. This slide here is, so I borrowed this from my ex-colleague and mentor, Fred Gassner. So this basically shows from the design down here on the left-hand side, all the way throughout the process until we start the construction, the timeline for verification, approval, procurement, manufacturing, transport to site, and the material CQA, and the range of timeframes for each of these basically steps. It can total up to 17 up to 38 weeks. So as you can see, this can take roughly 3/4 a year. So it is very important to have this timeline considered as part of the discussion between the project owners, the clients, and the designers. So we need to write the specification, prepare the specification and the design documentation, considering the requirements for the QA of the material before we can even start using the material for construction. Some consideration for QA regime in our specification. So when you prepare a specification, these are some of the factors you need to consider. Identify and agree Geosynthetics QC measures with the client early in design process. And this is again back to that timeline that I showed in the previous slide. Specification must be clear on requirements. So we see a lot of specifications that are not as clear as they should be. So essentially we need to make sure that the requirements are clear and they can be followed by the construction personnel. And also RFIs, request for information, or non-conformance reports, NCRs, during tender process, during procurement, and during installation. So we should somehow consider these RFIs coming through. But essentially the key there is we should try and raise the RFIs or close out the RFIs, earlier in the process, rather than raising those RFIs later during installation, which can cause delays and cost implications. So as I said, when we prepare the specification or design documentation, we need to also consider impacts on the project timeline and financial impacts. So we must consider, having a very good understanding of the timeline and financial impacts as we prepare the spec and design documents. So part 2, construction quality. So after material is conformed, material conformance is completed, we start the construction process. The topics I will cover here quickly are design to balance performance, cost, ease of construction or constructability. Preparing for lining, so that's the subgrade preparation. Destructive, non-destructive testing principles, so we talk about that. And liner integrity or leak detection survey is the other topic we will talk about briefly today. Site testing versus laboratory testing, and also documentation, the construction documentation. And at the end, we talk about variation from the design. So design for geosynthetics installation. We basically want, when we're doing a design, we want the optimal placement of panels, seams, and welding types. So panel orientation, we basically want to reduce the seams at the stress concentration locations. So it's very important to have that panel orientation and panel placement plans prepared before the installation, and have it discussed with the designer, with the CQA engineer, and make sure all of the criteria are considered for the panel placement plan. Creating a smooth liner at significant changes in grade. So that's to reduce the risk for bridging or wrinkles. And also minimizing the wastage. So important to minimize the wastage of the material and minimizing the seams as much as possible. Also anchoring. So anchor trench is a very important part of any CQA project. So we need to have clear specification about how the anchor trench should be constructed and backfilled. And again, panel placement plans and order of lining completion. So we've seen some contractors deciding to start from, say, the low point and then complete the lining towards the high point, or some other contractors decide to do it the other way around, start from the high point and finish at the low point. So that needs to be discussed, you know, if you want to line the batters first, floor second, or floor first, batters second. So there needs to be meetings and discussions between different stakeholders to make the best decision for the project. And also this last thing here is about blown film membrane creases. So that's a very typical issue that we talk about. When we use a blown film membrane, we need to consider those creases as we look at the panel placement plan, for example. Preparing for lining, which is the subgrade preparation. So some of the risks associated with the preparation of the lining is surface desiccation. So this is a very common issue on a lot of construction sites. We need to consider that. Risk of foreign material on a smooth prepared subgrade. So again, if the subgrade has any foreign material or any sort of sharp angle or any big size material included in the subgrade, that needs to be removed before the material goes in. Tire tracks as a traffic on the prepared subgrade, even a smooth drum roller that they use to make the surfaces smooth, that can also create, the drum can create marks on the subgrade. The question about how wet is too wet. So that's very important also to know what the moisture content should be on the subgrade, depending on what geosynthetic is going to be placed on top. Is it a GCL? Is it a geomembrane? And also the other important factor right at the bottom here is, are the material and equipment ready to go? So we see a lot of times that the construction for the subgrade is completed, but the material or equipment for the lining is not ready to go. Then it just takes a rain event to, you know, make a lot of damage to the subgrade and has to be reworked. Let's talk about destructive testing here. So on site, as we place the geomembrane material, for example, we do a lot of trial weldings, and how to prepare the as-built seam samples. That's another important decision to be made. Where to take these samples from, and what frequency of testing should be considered for the destructive testing, and also sample preparation for transfer to the lab. So these are the factors that we need to consider when we are deciding on the destructive testing. Specification needs to have clear guidelines in there to help the CQA engineer and the contractor to make best decision for the installation. So we have a good destructive testing regime for that installation. And also non-destructive testing. So some of these tests are listed here: spark or electrical testing, air lance or air pressure, which is called also a needle test, vacuum box, and as well as seam overlap trims. So again, the specification and design documentation must have adequate details around each of these non-destructive testing that can be adopted on site. And liner integrity survey. So this is becoming a very common exercise in most of the facilities we build in Australia these days. And in my opinion, it's a very good thing to see that after we take all of the care with the material conformances, with identifying the defects, also all of the CQA exercise during the installation of the material, there are still chances for holes or damages or tears in the material as they are placed during the construction. So if we do a liner integrity survey, LIS, we actually have a chance to identify those issues and also close out those issues before the facility is handed over to the client for commissioning. And from some of the recent liner integrity survey projects that our colleagues have been doing recently on some sort of critical and really big size projects, really showing us that, with all the care that we take during the construction, there are a significant number of holes and damages that these guys, the LIS guys, actually find after the construction is finished. So we talk about the right method for the site condition, if it's exposed, if it's covered. So we need to have a discussion around what liner integrity survey method we want to use for that particular installation. And it really depends on if the material are installed on the flat ground or on the slopes. Also, conductivity of the liner is an important factor to consider. We need to think about if it's a cell, a landfill cell, for example, if it's a leachate pond, if it's a coal seam gas water pond, brine pond, if it's a cap, or even if it's a tank. And depending on each of these applications, we can think about the best method to do a liner integrity survey. Isolation of the test area, sensitivity and the readings, anomalous readings, and also corrective actions. These are the other factors to consider when we are considering liner integrity surveys. On-site and off-site testing. So we know that conditions that can impact on-site testing results. So when we do any of these testing on-site, the field temperature, the maintenance of the mobile tensiometer, for example, and also water or dust in the weld, which we have seen actually these factors, all of them affect the quality of the seams very significantly. And also challenges with the laboratory testing. If you're taking destructive testing, send them to the lab and want to test them in the lab. So the time and cost associated with the sample transport, testing and reporting response time. So we need to consider that. And also when to use the archive sample and why, because with every DT sample we take, we also have archive samples. We need to make sure the archive samples are used properly and for a reason. In terms of documentation or as-built documentation, what should be recorded? So these are the main questions, and who should record it? So these should be actually documented in a specification. What are the requirements for the documentation? It's a specification or a designer's decision to ask for what should be recorded and who should record it. So that should be clear in the design documentation. Also, progressive sign-off on quality. That's an important thing because, if we see a failure in any part of the construction, there needs to be a procedure how we want to go back if it's now buried under several other layers. So that is the need for progressive sign-off on the quality. Also, we have seen like digital CQAs, QA engineers using tablets on site to record, to keep the construction records, or they do it manually. So we need to have that discussion at the beginning of the project and find the best solution for that particular project. Level of accuracy, how accurate we want the documentation to be, and also trackability of the material. So we basically want to know each roll of the material, where it has been placed in the construction. And finally, variation from the design. So we need to have clear agreements at onset of the project. So about those variations, what is our tolerances? What are acceptable tolerances? Because as envisaged versus as it happens, because the designers have envisaged something, what happens on site is something different. So we need to have that sort of link between the stakeholders so we can have a clear understanding. Design flexibility also is an important factor. A lot of times we see the contractors asking for so-called relaxation of the requirements in the spec. We need to have a clear understanding of the design intent, and also legislative process for each state needs to be considered. Equivalent material performance and level of environmental risk needs to be also considered. Authority to approve changes is an important factor. Who is authorized to approve a change on a construction site? And this whole thing is to minimize delay on site work and cost of the changes. So these factors are really important to consider. And the best is that they are actually documented as part of the design package. So when the contractor and CQA engineer and the designer and the client are having those stakeholder meetings about any of these particular items, there is clear direction or instruction given in the design documentation about how to resolve these situations. This is my last slide. And again, I've borrowed this from my ex-colleague and mentor, Fred Gassner. He put this in the 2019 ALTS conference in Brisbane. The bitterness of poor quality remains long after the sweetness of low price is forgotten. So I've finished my presentation with that. Thank you for listening. And we go to John now for his presentation.
Good morning, everyone. See if we can share the screen. Oops. Sorry, just wait for a minute.
So as John starts his presentation, just a quick note to everyone that you can use the Q&A tab to type your questions in there, please.
Good morning, everyone. Siamak asked me to give a CQA case history. So this is one of a geosynthetic reservoir for storage of hazardous liquid in Queensland. Just quickly introducing it, liquids are increasingly being stored in geomembrane reservoirs. We've got a long history of storing water, wastewater from municipal, industrial and agricultural processes, and relatively recently, hazardous liquids. Looking at the relative costs, geomembrane reservoirs are much cheaper than concrete or steel tanks. And this is leading to the storage of more valuable and also more hazardous liquids in these reservoirs. Now, to build a reservoir, typically you form earth bunds around the four sides of the reservoir, although sometimes people might use reinforced concrete. And you have a geomembrane liner and a floating geomembrane cover. And typically a 1 hectare area with a depth of 5 meters of liquid will give you about 50 megaliters of storage. And there are larger reservoirs with a gigaliter of storage. The liner has a design similar to a solid waste landfill liner, but often with leak detection between two geomembranes with a geonet leak detection layer in between. And in designing this, you've got to remember that the head of liquid in these reservoirs is greater than the head of liquid that's supposed to be in a landfill. And design of a floating cover needs ballast and floats and has to be shaped to accommodate the change in surface area of the contained liquid as it rises and falls. And the cover needs gas escape pathways and vents, man access ways, inspection hatches, etc. I won't spend much time on this because we haven't got much time, but there's all sorts of things you need to design for the liquid, the pipes and the pumps. For hazardous liquids, it's advisable to install instrumentation to automatically turn the pumps on and off to prevent overfilling of the container. And the cover is subjected to wind uplift, gas pressures, temperature changes, and needs durability for solar radiation and chemical resistance. So moving on to the case history. This is a caustic soda storage facility for mining, where we constructed 4 geomembrane reservoirs on reclaimed land in a mangrove wetland. near a coral reef marine park in Queensland for storage of 50% sodium hydroxide solution being unloaded from ships en route to the mine site. So due to the adjacent mangrove wetland and coral reef marine park, the prevention of leakage was essential. This is a view of the first of those reservoirs, and in the background is one of the steel tanks that it replaced because it was cheaper to use the geomembrane reservoir. It's a picture looking the other way over a couple that are being constructed down to the dock where the ships would come in and offload, and that's where the sodium hydroxide would arrive. The design of these particular reservoirs, earth bunds around all four sides. Each reservoir was 140 meters long, 60 meters wide, 4.5 meters deep, giving a storage capacity of 160,000 cubic meters. Now, on the base was a triple liner. We had a GCL on the base overlain with two geomembrane liners with a geocomposite leak detection layer in between the geomembranes. From memory, the lower one was 2 millimeters thick and the upper geomembrane was 2.5 millimeters thick. For the cover, we had a double geomembrane floating cover with a foam insulation layer in between, with ballast, floats, walkways, inspection hatches, and gas vents. So this is a picture during construction of two of those reservoirs. You can see the earth bund in the middle of the picture, and it goes around all four sides of each reservoir. At this stage of construction, I think we've got the first geomembrane in, and the leak detection layer is going in on the right-hand side, the white material. And then at this stage of construction, we're putting in the floating covers. So you can see the ballast and the walkways and the vents in this picture. Almost all of the welding was done using a double track wedge welder, except there was a little bit of extrude out welding needed around the edges of the tanks, as we call them, in places. It's another picture of the one of the covers, and you can see the walkway. Now that walkway is needed to get down onto the or get onto the cover for maintenance, to clear vegetation, and also we had two hatches in the cover to get to the hatches to take samples of the sodium hydroxide, but also because we put samples of the geomembranes, we suspended them in the sodium hydroxide for future testing. And that's another picture of the cover, and in the foreground you can see one of the vents. These are the pipes through which the sodium hydroxide enters and leaves each of these reservoirs. So they've been placed on the top liner geomembrane to be underneath the floating cover geomembrane. And you can see the pipes here coming up to a chamber, and then that's a finished chamber, and the metal pipe is how the sodium hydroxide gets in and out of this reservoir. As I said earlier, it's very important to have some kind of system for stopping that pump from pumping, so you don't pump up the reservoir and burst it with the contents. Right, moving on to QA/QC. There was extensive quality assurance and quality control measures during both the manufacture of the geomembranes and the construction of the reservoirs. Starting with factory inspections, I carried out the factory inspections for the geomembrane production because the geomembranes were produced here in Asia for the 4 reservoirs, including inspection of production, addition of additives, and laboratory testing of the membranes, taking samples for independent testing, and I carried out a review of the manufacturer's quality management system. Now, John Shears of Excelplast in Melbourne recommended hindered amine light stabilizers, or HALs, to be added to the membranes. HALs are resistant to alkalis because they do not undergo hydrolysis, and due to their high molecular weight, they're not easily extracted. Excelplast carried out the independent chemical resistance testing on the geomembranes after manufacture before installation was allowed. So until we got the results, resistance testing, the contractor couldn't start work on the site. These tests were carried out on coupons soaked in 50% sodium hydroxide solution in a forced air oven at 85 degrees centigrade for 21 days. The coupons were removed, washed in water and cut in half. One half was saved for analysis and the other given a second exposure to an additional 90 days. The first exposure was to determine extractability and chemical reactivity of the additives. The second exposure was to determine oxidative stability. And Excelplast carried out standard OIT tests, HPOIT tests, and determined that the coupons retained 63 to 100% of the HPOIT value. And so installation was allowed to proceed. So moving on to the site QA/QC, that was very thorough. In this picture we have, in the foreground is the contractor's QA/QC manager, and behind him is Keith Milne, who was the independent QA/QC supervisor. And I have taken this picture. I was there as well as overall supervisor of the QA/QC system. So we had a triple level of QA/QC on this very important site. The site inspection included all the normal things, earthworks subgrade, welding appearance and daily startup tests, weld tests, air pressure, vacuum tests. We did a huge amount of vacuum tests, more than you would normally see, and the normal peel and shear tests. And we took samples for independent testing. And there was very extensive QA/QC documentation. And then finally, we filled these tanks with water and carried out hydro tests on them. So just a few pictures of the QA/QC. You can see the regular air pressure testing of the double track welding. There you can see the needle into the space between the welds, and that's been pressurized, and that gauge is showing that a pressure is maintained for the required number of minutes. And the welder is recording the results as we normally do with a white pen. Unfortunately, this was a white colored geomembrane for the floating cover, but you can still make out the results here. So all the normal things that you do, but here it was being done to a very high level. I included this picture just to remind myself to tell you that we took all the destructive samples from just outside the edge of the reservoir. We didn't want to take any destructive samples inside the reservoir. Okay, now moving on to post-construction lab testing. As I said earlier, we suspended geomembrane samples in the caustic soda inside the reservoirs, and we extracted coupons at yearly intervals and tested them. After 5 years, based on the HPOIT values, the remaining service life was assessed, and the first reservoir was approved for continued use for another 5 years. So this is the, actually I think this is the second reservoir there. You can see the condition of it after 5 years. I went there to supervise the taking of the samples, and I also got to analyze the results. We had to walk out onto the cover, down the walkways and across the cover to take the samples out of the hatches, at which point I realized how important remaining service life is, because you don't want to fall through that cover into caustic soda. And this is a picture of the first reservoir after 5 years, and you can see that vegetation is beginning to grow around the ballast there. So the guy not only has to walk out to get the samples, but he also has to walk across this cover to remove the vegetation after a while. So wrapping up, cost effectiveness. Each reservoir was constructed for 1/7 the cost of a steel tank. To be cost effective, they needed to remain in service for only 4 years. The first reservoir was successfully in service for over 5 years and was then approved for use for another 5 years. And moving on to Siamak's mentor, the remaining service life of the other 3 reservoirs was assessed by Fred Gessner. So my conclusion, I see I'm just about in time. This was a very successful geosynthetics project. It was a testament to our industry that we could produce something like this to a very high quality. Okay, I'm going to stop sharing and hand back to Siamak.
Thank you, John. Very interesting presentation. So we are right on time. We have probably 2 minutes, and I suggest maybe we take 2 questions. One question that I sort of picked between the 7 or 8 questions that we have here is about the archive samples. So John, I think you also talked about several sampling or coupons that were taken from the material for different testing, and did you have archive samples taken and what that was used for?
Yes, we did. When we were looking at remaining service life, we went back to the archive samples as well.
Sure. So normally the archive samples are taken. So I think the question is, in what cases would you test them? It's when we have, some uncertainty with the actual testing that's been done on the main sample. So the archive samples are there if you want to do a retest or check something, or if there is a failure that we want to investigate. Also, there was a question about international accreditation for laboratories outside Australia, and if you have seen any issues. John, you can talk about your experience, but my experience is that so far we've done this for maybe at least 3 or 4 in the past couple of years. Facilities in the UK, in parts of Asia, Taiwan, for example, was one of them, and Germany. So far we haven't seen any issues. It's just that documentation process in the factory that needs to be quite clear right at the beginning before they start. So you must actually prepare clear instruction for them what you want from the sampling and testing to be photographed, and what needs to be in each, documented in each of those photographs, like the sample label, the serial number of the roll, the direction of machine or X machine direction. So all of those details has to be prepared in a sort of document and sent to the the overseas laboratory. And again, you can just check that ILAC to make sure that the lab that you're dealing with is listed in there on that ILAC document.
Yes, that's an interesting development, using independent laboratories in the country of origin of the material. It works reasonably well. I've found that it gets a bit difficult when the native language of the country you're dealing with is one particularly not using our script, and there are translations having to happen, and there can be some communication difficulties. So I have noticed that problem creeping in occasionally.
Yeah, absolutely. And like we said in the presentation, especially these days with the travel restrictions due to COVID, I think we obviously see more of that happening because there's not much travel.
But in Australia, you've got some very good labs.
We do, yeah.
Why not get samples taken and sent to your own labs, and then be able to communicate with your own labs?
Yeah, that's absolutely an option. So it's that decision to be made about whether we want to test overseas, or whether we take the samples and test in Australia, or whether we wait for the material to arrive in Australia, then we take samples here. So they are all the different methods that I sort of showed in my presentation. But project by project, I think we need to have that discussion and make the best decision for the project. Okay, so there are a couple of other questions here that we don't have time to get to those, but the good news is that all of them actually have names. So we have the details of those people who asked the questions, so we can definitely get back to them via email and respond to their questions, which we will do sometime the next couple of days. Before I wrap up for today, announcing again our hybrid event, 16th of June on the Gold Coast. So that's for people who are in Queensland or can travel to Queensland. For 16th of June, it's a one-day event in person, and it's going to be on the Gold Coast. We're going to have half a day, like morning sessions are online available as well, so people can, it will be broadcasted online. So we're going to have George Kerner presenting to ACigs about durability of geosynthetics material. We also have Nathalie Touz, Dr. Nathalie Touz from France, presenting to ACigs about sustainability in geosynthetics. So they're the morning sessions that can be accessed online as well as in person if you want to attend in person to the event on the Gold Coast. The afternoon sessions are a tour of the laboratory facility on the Gold Coast, and also a panel discussion about material durabilities that will be held in that in-person event. So the details are on the website. I encourage everyone to check the website and make sure you register for those events. Thanks, John, again for your contribution to this presentation. It was really nice to have you, and hopefully in the future we can arrange more presentations, more webinars with you.
Thanks for inviting me.
Thank you. Thanks to the audience as well, and we'll see you in our next event. See ya.